Partitioning and divide and conquer strategies, numerical integration, and the gravitational n-body problem. Adapted from Parallel Programming by Barry Wilkinson and Michael Allen. In this lecture, we will discuss numerical integration using two different ways, by rectangles and by trapezoids. We'll also look at adaptive numerical integration and look at the example of a gravitational n-body problem. Recall from the last lecture the example where we divided the problem and solved each subproblem. The problem was assumed to be divided into equal parts, and simple partitioning was employed. Sometimes, simple partitioning will not give the optimum solution, especially if the amount of work in each part is difficult to estimate. For example, with bucket sort, it's only effective when each region has approximately the same number of numbers. A general divide and conquer technique divides the region continually into parts and lets some optimization function decide when certain regions are sufficiently divided. Let's look at a different example, numerical integration, on the next page. When we talk about integrating a function like this, we are talking about computing the area under the curve. So when we're trying to do this, we can divide the area into separate parts, each of which can be calculated by a separate process. Now, each region could be calculated using an approximation given by a rectangle, for example, where f of p and f of q are the heights of the two edges of the rectangular region, and delta is the width, or the interval. The complete integration then can be approximated by the summation of rectangular regions from A to B by aligning the rectangles so that the upper midpoint of each rectangle intersects with the function. This has the advantage that errors on each side of the midpoint tend to cancel each other. So in this particular example, you see that the width of the rectangle is related to the number of partitions by this formula delta equals b minus a divided by n. So for the ith rectangle, the area is the function of a plus delta I plus delta over 2 times delta, because delta is the width of each partition. Therefore, the whole area under the curve is given by this summation, which is the sum of each one of these rectangles that we've divided the curve into. Let's look at a specific application of this. Now, from mathematics, we know that if we use this formula, we can calculate the value of pi by taking the definite integral from 0 to 1. So, if we can calculate this yellow area, this means that we will have computed the value of pi. Here is a standard sequential C program that could be used to implement this. In the main program, we see that we ask the user to input how many partitions, that is, how many slices we want to slice the area under the curve into. And then we call this pi calculating function and print out the result. This is the function that was called from the main function in the previous page. In this function, it takes the number of partitions and then figures out that each step is going to be 1 divided by the number of partitions. After that, it goes through a loop through every single partition, calculating the area of each partition. So if you look at the inside of the for loop, it figures out that the middle of each partition is step divided by 2 plus step times I. Why step divided by 2? Because that gives us the middle, and step times I gives us which partition it is. So then we add to the total the function at that point of x, the function being 4 divided by 1 plus x squared, just as we saw in the earlier screen. So how do we convert this into MPI in order to have it calculated in parallel? Well, the function f remains the same, but the function pi will need to be modified to take into account which part of the function should be calculated. We are going to do this calculation by alternating the slices between each process. So look at the for loop. You see that we're going to start at rank. Rank, if you recall, tells us what process number I am. And then you see that the increment is I plus equals NP. That means each time round, I'm going to increment the number of processes. So I will skip the slices that will be calculated by other processes. The inside of the loop is just the same. You calculate the area of the slice that you're going to calculate, and we add it to the total. At the end, we return the total to the main function. The main function is going to have to put all these totals back together to form the actual value of pi. So here is the main function. You see that we had to add the MPI constructs like MPI init, MPI com size, and MPI com rank. MPI init to set things up, ready to go. MPI com size to figure out how many processes are in our communicator. And MPI com rank to figure out who am I. So the first thing is only process 0 should ask the user for how many partitions. So we say if not rank, that means if rank is 0, calculating pi, how many partitions? We ask the user. Then we need to transmit this number, num partitions, to all the other processes, which is why we have this MPI bcast, which is a broadcast, so it sends it to everybody. Now, we call the pi function and we get our partial result. That is, each process has a partial result. We call this local result, and then we call MPI reduce to reduce all the results using the MPI sum, meaning add everything together, which will give us the result, which is pi. So now, if I am process 0, I print the result of pi. And finally, we call MPI finalize to tell MPI, okay, we're done. In order to help you to visualize and understand this better, we have made an animation that illustrates what is going on in this program.
How to calculate pi using rectangular quadrature. From mathematics, we know that if you calculate the definite integral from 0 to 1 of 4 over 1 plus x squared, we will get the value pi. Here is the portion that we would have to calculate the area for. If we divide the shape into 4 parts, like this, so we take the value of the function in the middle of this portion, that is, at 0.125. This rectangle gives us an approximation of the area under the first part of this curve. The height of the rectangle is calculated by replacing x with 0.125 in the formula. The result is 3.9384. The area of a rectangle is width times height. This gives us an area of 0.9846. Now we go on to the next section. We repeat the process by taking the middle of the second section, forming the rectangle of the height in the middle. The height is 3.5068. The area is 0.8767. Now we proceed to the third section. And we do the same thing. And we find the approximation of the area here is 0.7191. And now for the last section. Which gives us 0.5664. Now we've got all four sections. We sum them up and get our approximation for pi. Obviously, the result is not that accurate with only 4 divisions. The more divisions you make, the more accurate it becomes. The following animation shows what happens if we run the MPI pi calculation program using 4 processes. All 4 processes start running at the same time. Each process has its own set of variables from the program. The number of processes in our example is 4 and is the same for every process. Initially, the only difference between the processes is the rank. Interaction with the user, or input-output, is usually only done on the process with rank 0. In a real calculation, it would have many more than 100 partitions, but in this example, to keep the animation manageable, we shall choose 100 partitions. Process 0 then broadcasts the number of partitions to all the other processes. Every process then calls the pi function with the num partitions. Each process calculates the same step size. This is because such small calculations usually take less time than having process 0 calculated and then send it to every other process. Each process starts with a different I, which is based on the process rank. Because each process has a different I, it then calculates a different X, and so subsequently a different total. Each process then increases by the number of processes. This ensures that each process does a different slice of the curve. Now I is still less than num partitions, so we continue the loop. Each process then proceeds with a new I, which generates a new X. and hence adds to a new total. And now for the next round. Now I is still less than num partitions, so we continue the loop. Finally, I is no longer less than num partitions. So we calculate the subtotal for this rank and return it. The numbers returned from the function pi must be entered in local result. The numbers are: for 0 is 0.792876. For 1 is 0.787926. 2 is 0.782924. And for 3, it's 0.777874. Then finally, the MPI_reduce collects those 4 local results and adds them together, and puts the total in result in process 0 equals 3.141601. Process 0 prints pi is approximately 3.141600 986 923 1245 0000 using 100 partitions.
To help you understand this better, here is a video by Patrick JMT, which I found on YouTube.
Okay, in this video we're going to talk about approximating the value of a definite integral using n rectangles. So this is going to be a follow-up to kind of the general idea of the definition of a definite integral. But here again we're just approximating. So the idea is we've got some function y equals f of x. We want to find the space between the curve and the x-axis. Again, we need to remember that when we calculate the definite integral, if the area is above the x-axis, it'll give us a positive value. And if the area is below the x-axis, it'll give us a negative value. So we're trying to find this area. For example, the idea is maybe I could use right endpoints. So for this first interval, I would pick the right endpoint, follow it up till it hits the graph. That'll give me a rectangle. I'll go to the next interval, make a rectangle, I'll calculate its value, and I'll do this for every interval. Okay? So obviously the number of rectangles that you end up using is going to be somewhat arbitrary. The main idea being, though, the more rectangles you use, the better the approximation becomes. So in this problem, I want to approximate the area, the definite integral from 0 to 2 of 16 minus x squared. Remember, 16 minus x squared is a parabola that's flipped upside down and has a y-intercept of 16. And I've just arbitrarily chosen 4 rectangles and left endpoints for my first example. So since we're calculating the definite integral from 0 to 2, we're talking about this blue shaded in area. Okay, so that's what we need to calculate. Okay, the first thing we need to recognize is we're going to chop our rectangle up into 4 pieces. So what's the width of each piece? Again, well, we label the width to be delta x. Remember, that's b minus a over n, b being the upper limit of integration, a being the lower limit of integration, n being the number of rectangles you use. So we'll get 2 minus 0 over 4, which is 2/4, or a half. So that means if we chop this up into 4 pieces, each interval has width 1/2. So the first point will be 0.5, then 1, then I'll have 1.5, and then the x-coordinate of 2. Since I'm using left endpoints, again, when I look at the first interval, I'm going to use the left endpoint. I'll make a rectangle. I'll do it for the second interval. I'll make a rectangle. I'll do it for the third interval, make a rectangle, and for the fourth interval, I'll also make a rectangle. So we have to calculate the values of these 4 rectangles, and that'll be an approximation. In this case, just by the shape of the graph, notice it's going to be an over approximation because my rectangles are going to give me a little bit outside of the region. So it's easy enough to calculate. These problems, if I can say about anything in calculus, these are easy problems. At worst, they're going to be computationally tedious. Okay, so the area is going to be roughly equal to the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3 plus the area of rectangle 4. Okay, so to calculate the first rectangle, the area of it, we know that it has a width of 1/2. To get the height corresponds to the y-coordinate. Again, we're using the left endpoint, so we need to plug the x-coordinate of 0 into our function, and that'll give us the area of the first rectangle. Now I need to figure out the area of the second rectangle. Again, the width of it is 1/2. That's our delta x value. To get to get the height of the rectangle, we need to plug 1/2 or 0.5 into our formula. To get the area of the third rectangle, we'll do the same thing. Again, it has a width of 1/2. To get its height, we plug 1 into the function. And for the last one, we'll plug, again, a width of 1/2, and we'll plug 1.5 in to get that height. The only thing we really have to compute are the f of 0, f of 1/2, f of 1, and f of 1.5 values. So we'll get 1/2. Again, if you plug 0 into our function, 16 minus x squared, we'll simply get 16 plus 1/2. Now we'll plug 1/2 into our function. So we'll get 16 minus 1/2 squared. Plus 1/2, we plug 1 into our function. We'll get 16 minus 1 squared. And I'm going to run out of room. Our last rectangle will be 1/2. And again, all you have to do now is plug 1.5 into your function. Okay, and that'll give us the area of the fourth rectangle. So I didn't actually calculate these. Sorry, ladies and gentlemen, I was a little bit lazy. But this is going to be the setup. At this point, if you're taking calculus, it should just be arithmetic, and I have full faith that you can simplify that down. Okay, but again, this is going to be an overestimate in this case, just based, basically just based on the shape of the function. Again, so using left endpoints is completely arbitrary. So let me set up just maybe one other example. If I can do that real quick before my time runs out. So again, 16 minus x squared, we're going to use the same function. We'll go over to 2, so here's 16 minus x squared. Suppose now that instead of using left endpoints, we use midpoints from each interval. Okay, again, everything stays the same. There's only going to be a slight little change in what happens. Okay, so we still chop it up into 4 pieces. So this is 0.5, 1, 1.5. But now to get the heights of our rectangles, if we use midpoints, well, we just have to use the midpoint of each interval. So this would be the midpoint 0.25. This would be the midpoint 0.75. This would be the midpoint 1.25. And this would be the midpoint 1.75. So make a mental note of those values. I'm going to erase them just so my picture doesn't get too cluttered. But again, that's the midpoint of each interval. Okay, so now my rectangles, though, are going to extend up to the middle of each interval. So notice in this case, again, my artistry is a little bad. If you were to have a good graph of 16 minus x squared, you would see on the left side you would get a little underestimate, and on the right side of the interval you would get a little overestimate. So I think our midpoint approximation would be better than using, say, left endpoints or right endpoints. But again, that just really depends on the geometry, the shape of your function. Okay. In general, midpoints will give you better approximations as a rule of thumb, but there's certainly counterexamples to that. Well, again, everything's the same. We're still adding up areas of rectangles. Rectangle 1 plus rectangle 2 plus rectangle 3 plus rectangle 4. The only thing that's changed, the width is still the same, but to get the height, notice from the first interval, that's from 0 to 0.5, well, the midpoint is going to give me the height of the function, so I would need to plug 0.25 in. My second rectangle, I would have 1/2 times, I would take the midpoint, which would be 0.75, so I'm writing too big here. Rectangle 3 would have width 1/2. To get the height of it again, we would plug the midpoint in, or 1.25. And for the last rectangle, that's 1/2 f of, now again the last midpoint would be 1.75. And lastly, you would have to plug this in. This is where it would be real tedious. So 1/2, you would have to plug 0.25 into your function. So 16 minus 0.25 squared, whatever that is, plus 1/2, we plug 0.75 into our function. 16 minus 0.75 squared, excuse me, plus 1/2. We need to plug 1.25 into our function to get the height of that third rectangle. 16 minus 1.25 squared. Last but not least, our fourth rectangle has width 1/2, and 16 minus 1.75 squared. Again, whatever that works out to be. So these problems, again, are very tedious. But the good thing is they're relatively straightforward. If we used 4 rectangles and right endpoints, notice we would use the values 0.5, 1, 1.5, and 2 to get the heights of our rectangles. And in that case, it looks like it would in fact be an underestimate. So I hope this makes some sense. Sorry I didn't compute all the numbers for you. You all can take a look at that. If you have any questions, shoot me an email and I'll try to sort it out for you. Alright, good luck out there.
Another way to do numerical integration is using the trapezoidal method. In this method, instead of dividing each slice into a rectangle, we divide each slice into a trapezoid. Prior to the start of computation, then, each process is assigned to be responsible for computing a different region. By making the intervals smaller, we come closer and closer to getting the exact solution. Since each calculation is of the same form, the SPMD model is appropriate. Suppose we were to sum the area from x equals a to x equals b using p processes numbered 0 to p minus 1. The size of the region for each process is b over a divided by p. To calculate the area in the described manner, a section of SPMD pseudocode could be as shown as in the next slide. Here we see the pseudocode. For each process I, if I'm the master, then I'm going to ask the user for the number of intervals. Then I need to broadcast this result to everybody else. Now, each process then will figure out its region by using this formula, b minus a divided by p, for the length of the region. Then, the start of the region is a plus region times I, and the end of the region is the start plus the region. Now, the size of the interval is b minus a divided by n. So we start out with the area initialized to 0, and we go from the start to the end and calculate the area of each trapezoid, adding that to the total area. Then we need to divide by 2 because the formula for the trapezoid is a plus b times d divided by 2. So here we have the 0.5 multiplication. And then we perform a reduction to add up all the results. Now I'm going to show you another video by Patrick JMT to explain this same concept.
Okay, in this video I'm going to do an example using the trapezoidal rule. And all this does is you're approximating the area underneath a curve using trapezoids. Sometimes you'll use rectangles. Just another way to do it is to use trapezoids. Without doing a lot of justification, basically the formula is this. It says you can approximate an integral from a to b, some function. It says basically what you do, assuming we chop it up into n pieces, okay? It says we take delta x over 2, which is just the length of the interval divided by the number of pieces. Then it says we just take the function evaluated at the first point plus 2 times the function evaluated at this next one. Notice the 2's all inside of here until the very last point. Notice that doesn't have a 2 on it. Again, where x sub I is given by this formula a plus I delta x. Obviously, this is probably not the place you want to start if you know, you're just now looking at integration. But if you've seen the video about that I did about understanding the definite integral, I think this x sub I and this delta x notation should be familiar. So I'm going to make mine relatively straightforward just to hopefully make the numbers work out a little bit better. So it says we want to approximate the integral from 1 to 5 of 1 plus x squared, and I'm going to use 4 trapezoids. If you were to graph 1 plus x squared, so I'm just going to draw a little picture here. 1 plus x squared would be a parabola shifted up 1 unit from x equals 1 to x equals 5. And it says we're going to chop this up into n pieces. Okay, so delta x is going to have value b minus a, so that's the right point minus the left endpoint, divided by the number of rectangles, so we'll get 4 over 4, or 1. So that's the width of each one of our intervals. Again, we've chopped our interval from 1 to 5 up into 1, 2, 3, 4 pieces. Each one has width 1, so you can see that, okay, well, the values would be 2, 3, and 4 of our points. And it says now what we're going to do is we're going to use, again, trapezoids to just kind of cover this region and approximate the area of underneath the curve using these trapezoids. Okay, so my bad little picture there. Okay, so it says according to this formula here, so again, we know value delta x is 1 in this case. It says our formula, it says we take delta x, okay, so delta x over delta x over 2, and then we multiply that again by f of x sub 0. We multiply the next ones by 2 until we get to the very last one, which only has a 1 attached to it as well. Okay, so if we fill all of this information in, it says the integral from 1 to 5 is going to be roughly equal to the value of delta x, which is 1. We divide that by 2. And then for my points, the first point is going to be our x sub 0. The last point generically, that's your x sub n. And this would be your x sub 1, x sub 2, x sub 3, x sub 4, or the last one. So it says we have to take f of 1, but then it says we have to take 2 times the value of, when we plug in our second point, 2, and then we'll get twice f of 3, excuse me. We'll also get 2 times f of 4, and then the very last value, f of 5, that doesn't have a 2 in front of it, so I ended up squeezing that in here a little bit. Let me copy it down here. So we'll get 2 times f of 4 plus the last point, f of 5. Okay, so this is now just a bunch of tedious arithmetic more than anything. So let's calculate all of this out. So I'm going to get rid of my pretty picture here. You know, so any of these approximating rules, trapezoid, midpoint, left endpoint, right endpoint, it's just a formula you've got to remember, and then it's just really tedious, okay? So, again, the function I'm using here is 1 plus x squared. So my f of x is 1 plus x squared. So it says this integral is going to be roughly equal to 1/2 Okay, when we plug 1 into our function, we'll get 1 plus 1 squared. 1 squared is 1, so we'll get 1 plus 1 or 2. Then it says we get twice the value when we plug in 2. Notice if we plug in 2, 2 squared is 4, 4 plus 1 is 5, so we've got to double that value. When we plug in 3, 3 squared is 9, plus 1 is 10. Again, we have to double that value. F of 4, when we plug 4 in, 4 squared is 16 plus 1, or 17. And again, notice the last point, F of 5, that doesn't have a 2 in front of it. When we plug 5 in, 5 squared is 25 plus 1, so 26. And now we just have to add all of this stuff up. So again, this was our f of 1 value, f of 2, f of 3, f of 4, and our f of 5 value. Okay, so alright, we're almost there. What do we get? So this is 10 plus 20 plus 34 plus 26. 34 and 26 is 60 plus 20 is 80, 92. So it says we get 1/2 of the value 92, which I do believe is the number 46. So it says the area underneath the curve 1 plus x squared from 1 to 5 using 4 approximating trapezoids would be roughly equal to the value 46. Okay, so again, this is just a matter of knowing a formula, you know, a tedious, I don't know, maybe a slightly tedious formula. Again, if the function is at all complicated, or, you know, they make you use a lot of regions, if they make you chop your interval up into lots of pieces, clearly this computation is going to be very tedious. But again, the main thing to catch with the formula is the delta x over 2, and then just notice the 2's in front of all the stuff in the middle when you're evaluating the function. So, alright, I hope this video helps. If you have any questions, feel free to post comments, and hopefully either me or somebody else can help you out.
Up until now, we have always divided each slice in the same manner. That is, each slice has the same size. However, there are situations where you have a curve that is changing very rapidly in part of the curve, whereas changing very slowly in other parts of the curve. If that is the situation, then it makes sense for when it is changing rapidly that you slice it thinner, but when it's not changing as fast, you slice it bigger. So in this example, we have 3 areas A, B, and C. The computation is terminated when the area computed for the largest of the A and B regions is close enough to the sum of the area computed for the other 2 regions. So if you can see, as C becomes smaller and smaller, that means that we don't have to slice it any further because the approximation is already pretty good. So we do adaptive quadrature because we are trying to make the computation of areas under slowly varying parts of the curve stop earlier than computations of areas under more rapidly varying parts. So we use this trick with the reducing the size of the C until we say, okay, it's good enough. Another issue to consider is that as the spacing of delta varies across the interval, this means that we cannot do a fixed process assignment because that will not lead to the most efficient use of processes. So we need some care in choosing when to terminate. This method of deciding to stop could have the risk of false termination. What do we mean by false termination? Well, consider this picture where you see that we happen to find that the value at each edge of the A and B boxes are the same, but we don't realize that inside the A and B boxes, the curve actually is doing something different. So, if that happens, we are fooled to thinking that, oh, we've already got a really good approximation and we should stop. Now let's take a look at this video by Jacob Bishop, which also explains how adaptive integration works.
The other methods that we've talked about so far have always used equally spaced points. And so I've drawn a function here so you can see an example of when that might not be a good idea. So we have this function that is relatively unchanging for a period of time, and then it changes rapidly, and then it doesn't change again. Well, if we use equal step sizes, then we're going to have to use a small enough step size that we can capture this behavior in here. And so we've got to really, really divide it down because until we get a small enough step size that we really do a good job of capturing this behavior in here, our integral is going to be off. The other thing is we may not even detect that it's off. So that's something that requires a little bit more thinking. And if you look here, really using just one step, like between here and here, would be fine. And then using one step between here and here would be fine. Like even the trapezoid rule would do pretty good there. And then if we just refine the number of steps that we use right in this area, then that would be a lot more efficient. And this is actually exactly what adaptive quadrature does. And it refines the step sizes in areas or in regions where the function changes rapidly. And this is how it works. So I've drawn a couple of functions here, and we're going to start out with exactly the same thing that we've been doing. So we have an interval a to b where we want to estimate the area under this area and the region between a and b, and we can do that with a step size of h1. So I've depicted the step size here as h1, and we're just going to call that IH1, just like we did before. But here we're going to use the Simpson 1/3 rule instead of the trapezoid rule, which we used in the Richardson extrapolation example. So we're going to use the Simpson 1/3 rule for this, and then we can refine the step size, right? We can, on the same interval, same function, we can refine the step size to 1/2, and then we can do apply Simpson's 1/3 rule to each portion of this. So we do the composite Simpson, or the multiple application Simpson's 1/3 rule, and we can get an estimate for the integral of this, and we can call that IH2, and we have IH1. And just as we did in Richardson extrapolation, we can come up with, and I've shown this here, we can come up with an equation for the error based on the integral at h1 and the integral of h2. We come up with this equation for the error. So we can represent the error, and this time rather than using the error estimate for refinement, or for refining our estimate, which we will do, but not until after we've checked the error. So we check the error of h2, the error of in the integral represented with h2, recalling that I equals I h whatever plus e h. So the integral is equal to the estimate plus the error, and so we're estimating the error here as 1/15 IH2 minus IH1, and so this is the error estimate for doing the Simpson 1/3 rule and then a multiple application Simpson 1/3 rule with half the step size. So then what can we do? Well, we compare that error and we say, is this error less than some threshold? And if it's a low enough error, we're done. And obviously in this example, it would be pretty good. But if it's not low enough error, then we do it again. And so then we will go, so we had gone before here having the step size, we're going to go again and we're going to half the step size again. But when we half the step size again, we're just going to half the step size then for each of these regions here. I'll call that region 2 and region 1, and we half the step size, so then we look at the estimated integral for region 1 and compare it to the integral that we estimate with a half step size for region 1, and if that's good enough, then we get our final integral estimate for region 1, and if this one's good enough, then we get our final integral estimate for region 2, and we're done with each subregion just with one more refinement. But if it's not, then we apply this all over again, and you can see how they will get smaller and smaller, but only for the regions where the error is above our tolerance. Now, the other thing I'll note here is that we actually do, after we compare our error, we actually do use this error estimate in computing our new integral estimate. We do say that I is equal to, and of course it's just approximate, but that's our best estimate of our integral, then will equal I H2 plus 1/15 I H2 minus I H1. And the other thing that we need to note here is that this equation right here actually turns out to be exactly Boole's rule. Boole's rule. So and so after that, if we have low enough error, that's when we stop.
Here is another use of parallel processing, the n-body problem. The n-body problem comes about because it becomes very computationally complex to calculate more than 2 or 3 bodies in terms of gravity. So we're trying to find the positions and movements of bodies in space, like planets and satellites and so on, and we are calculating it based on the gravitational forces using the formula F equals gma mb divided by r squared, which tells you the gravitational force between two bodies, ma and mb. G, of course, is constant, is the gravitational constant, and r is the distance between the two bodies. So how much force is applied on these bodies? F equals ma, where m is the mass of the body and F is the force, a is the resulting acceleration. So from this, we should be able to calculate what happens next. We do this calculation by doing step-by-stepping of the time. So if the time interval is delta t, then if the mass of the body is m, the force is given as this: mass times velocity of t plus 1 minus velocity at t and divided by the delta t. So this gives us the new velocity at t plus 1, that is velocity of t plus f of delta t divided by m, where t plus 1 is the velocity at the time t plus 1 and vt is the velocity at time t. So that means that over this interval delta t, the position changes by x to the power t plus 1 minus t equals v delta t, where x to the power of t is the position of the time at t. So we stepped the bodies and the forces change, and then you have to repeat this computation. So for a normal three-dimensional space using XYZ coordinate system, the distance between two bodies A and B is given by this formula. R is the square root of xb minus xa squared plus yb minus ya squared plus zb minus za squared. So each of the directions of the force is given by these formulas. Fx is gma mb divided by r squared times xb minus xa divided by r squared. Similarly, for Fy, just replace the y, and Fz, replace the z. So the MA and MB will have the coordinate XA, YA, and ZA, and XB, YB, and ZB. So turning this into code, we would need nested for loops to calculate each time period and then for each body, and to calculate the force for each body and the new velocity resulting from that force, and then move to the next position, and then for each body we update the velocity and position. Now you see that due to this nested loop, this algorithm is actually an O of n squared algorithm for one iteration, as each of the n bodies is influenced by each of the other n minus 1 bodies. So if you've got a lot of bodies, where n is very large, this direct algorithm is going to be very time consuming. One way to try to reduce this time complexity is by noting that when you have a distant cluster of bodies, it can be approximated as a single distant body of the total mass of the cluster situated at the center of the mass of the cluster. So, as is illustrated in this picture. Another way to try to reduce the time complexity is the Barnes-Hut algorithm, where we start with the whole space in which one cube contains the bodies or particles, and first this cube is divided into 8 subcubes. If a subcube contains no particles, the subcube is deleted from further consideration because there's nothing there to compute. If a subcube contains more than one body, then we keep dividing until every subcube contains only one body. And this results in an octree, that is, a tree with up to 8 edges for each node. The leaves represent cells, each containing one body. After the tree has been constructed, the total mass and center of mass in a subcube is then stored in each node. So for a two-dimensional problem, each recursive subdivision will create 4 sub-areas and a quad tree, as shown in this picture. So in general, the tree will be very unbalanced, and the three-dimensional case is basically the same idea as this picture, except that you have up to 8 nodes for each 8 edges for each node. So that means that we can calculate the force on each body obtained by traversing the tree, starting at the root, stopping at a node when the clustering approximation can be used. That is to say, when r is less than d divided by theta, where theta is a constant, typically 1 or less. Theta is called the opening angle. And constructing the tree requires a time of O of n log n, and so does computing all the forces. So the overall time complexity of the method is O of n log n, which is much better than O of n squared, which was what happened with the brute force method. Now the problem with that previous method was that it created an unbalanced tree. So people came up with another way called the orthogonal recursive bisection, which is illustrated in this picture here. This is of course a two-dimensional version, but you can extrapolate it to a three-dimensional version. So first, you have a vertical line to divide the area into 2 areas with an equal number of bodies. Then, for each area, you do a horizontal line to divide it into 2 areas with an equal number of bodies. And you keep repeating this until there are as many processors. Then one processor is assigned to each area, so every processor has the same number of bodies to deal with. So this actually helps you to divide the problem between many processors. Here is a video that shows you an example of the calculations resulting from this n-body problem calculations. This video illustrates how you can simulate an entire galaxy of stars